Hello, everyone. Welcome to the discussion on cities, air quality in cities. In this discussion, we'll be talking about air pollution, its sources, chemistry, and health impacts, majorly on the cities as well as on the larger geographies beyond cities. I'm Sunil Daya. I'm an analyst at Center for Research on Energy and Clean Air. I have been working with Greenpeace. I have worked with Greenpeace for about 8 years, and my role at Greenpeace India and Greenpeace International was of a strategist and research analyst. I basically focus on energy and air pollution issues, and interest lies in the energy transition to cleaner fuels, achieving the breathable air quality goals across India as well as globally. Right now, I'm working as an analyst at Center for Research on Energy and Clean Air. This is a group based out of Finland, and we are present in several geographies across South Asia, Southeast Asia, East Asia, as well as in Europe. And we primarily look at health impacts of energy sources and air pollution policies across the globe, and try to help the governments, campaigning organizations, as well as research institutions in putting out facts and scientific evidence to move towards clean air and breathable skies to achieve the goal of energy transition. Today I'll be having a discussion with Professor L.K. Hattig, as well as Dr. Hang Su and Dr. Gulia. I'll briefly introduce all the panelists, and then we can go into a round of presentations by each of the speakers, which will be followed by a question answer session, and then we'll be going into uh, answering the questions by the participants as well. So, Professor Dr. L.K. Hertig operates at the intersection of health, science, and environment, and was recently appointed to a Heisenberg professorship at the University of Augsburg. She's a geographer by training and has expanded her research to include the health impacts of atmospheric and environmental factors, undercurrent, and future climate change scenarios. Her research focuses on regional and local climate change, statistical downscaling, temperature extremes, air pollution, in particular ground level ozone, vector-borne diseases, and urban ecology. Thank you, Dr. LK. We are delighted to have you as part of the discussion. Moving on to Dr. Sunil Gulia. Dr. Sunil Gulia is currently working as a senior strategist in CSIR Nehru Delhi Zonal Center, which is one of the premier research institutes, government research institutes in India. He has more than 10 years of working experience. He has more than 10 years of working experience in the field of air pollution, while working on CRRI, IIT Delhi, and NERI. His area of interest are urban air quality management, air quality modeling, source apportionment, and environment impact assessment. Thank you, Dr. Guliar, for being part of the discussion, and we look forward to hear from you in terms of your experiences and research, particularly in terms of air quality and its impacts in India. Moving on to the third speaker, Dr. Hang Su. He is the head of Aerosol Cloud and Surface Interaction Group at Max Planck Institute for Chemistry, Germany, and a visiting professor at the Shanghai Academy of Environmental Sciences. He received the Arne Richter Award for Outstanding Young Scientist from European Geosciences Union. Hang Su's research addresses a key current topic in atmospheric sciences, multi-phase interactions, and their influence on the atmospheric chemistry and cloud microphysics. Thank you, Dr. Hangsu, it's a privilege to have you on the panel because you'll also be speaking on one of the most critical issues which is ongoing in India, which is aerosol and their chemical transformation and contribution to the pollution, and we look forward to hearing more from you. So, without wasting much time, I would like to move on to our first speaker, Dr. L.K. Hertig. and I would like to request her to present her work in next 15 minutes, and after that we'll be moving on to Dr. Sunil Puria. So over to you, Professor L.K. Hartley. Thank you.
Very much for the introduction, and I would like to talk to you about the topic of urban ozone pollution, heat and health. And so what can you expect in the next 15 minutes? I would like to tell you something about the relationship between ground level ozone pollution and health. And then a couple of things about ozone in India. It's a problem not only in Europe, but also in Asia. And then I come to the European part and would like to combine the ozone pollution with heat events, and then a couple of things about ozone in urban areas and some future research directions. So I start with the health impacts of ground level ozone. And first of all, we have to distinguish two different types of ozone. So for once, we have I call it now the good ozone, which is the stratospheric ozone in the stratosphere. And it's our protection from the strong UV radiation. And on the other hand, we have the bad ozone, how I call it now, and it's the tropospheric ground level ozone, which is secondary built through reactions. And there are a couple of health impacts related to ozone. And ozone is something which is not that well known compared to, for instance, particulate matter or nitrogen oxides. But ozone affects mostly the lung functions, and it's also connected with inflammation responses. And then we see respiratory symptoms and also an increase in the medication use and asthma attacks, particularly also in children. And then it can go up until you have to go to a hospital, or even death rates are related with a high ozone pollution. So show you an example of the relationship between ozone and myocardial infarction frequencies. It's for the city of Augsburg, which is a city close to Munich, and we have a very good register data here. And you see the cumulative exposure response association of the daily maximum 1 hour ozone concentrations with the myocardial infarction frequencies in the city for the summer month. In Germany or in whole Central Europe, the highest ozone concentrations usually occur in spring and in summer. And we see an increase of the myocardial infarction frequencies until about an ozone concentration. It peaks here at around the 75th percentile, and it's about 120 micrograms per cubic meter air. And then it declines again, but also it stays significant until about the 90th percentile. And these are ozone concentrations of about 140. So we have a significant relationship with the heart infarction frequencies. And if we recall that the current standards of ozone, the thresholds, the health thresholds, they are at in Germany at 180, and this seems much too high in this case. I come now to ozone pollution in India, and I just want to show you a couple of aspects here. First of all, we have the highest ozone concentrations in India in the winter time. And this is in contrast to Central Europe, where we see the highest concentrations in spring and summer. And we see here it's a study which relates now the ozone pollution with different sources where they come from. And in all seasons, the transport sector plays a significant role for the buildup of ozone, but also biogenic sources. And in winter, this is the first column here, you see that the residential sector also plays a significant role. So if we look now a little more in detail into one example, I show you here a study for Daly, and it shows here in the pictures the back trajectories of the volatile organic compound emissions. Volatile organic compounds are a precursor element for the buildup of ozone and also nitrogen oxides. And here you see now the colors show you the concentrations of the volatile organic compounds, and you see the trajectories, one for June and the other one for November. And what I want to tell you here is that long-range transport of the precursor emissions play an important role for the ozone concentrations at specific cities. So we have, for one, a background flow into the area and also an in situ build-up. And since in this case, the NOx concentrations are already so high, they don't contribute to further increases of ozone concentrations. But if you introduce volatile organic compounds at precursors, you get a further O3 formation. And where do these volatile organic compounds come from? They are mostly emitted from traffic and in situ in the city itself, but also from other sources, in the case of June from the southeast, or in case of November from the northwest. And interestingly, if we now act on air pollution to reduce, for instance, particulate matter, it may reduce particulate matter, but it can lead to an increase in ozone, because then we have an enhanced solar radiation into the area, and it's a photochemical reaction in ozone buildup. So we enhance the ozone concentrations, and also a weakened removal of hydroperoxide radicals on the particle surfaces may contribute to an increase in ozone. So now I want to switch the region and come to Europe and show the ozone problematic combined with temperature. And why do I want to go now on these combined extremes? They are related very closely. Often when we have high temperatures, we also have high ozone concentrations. For one, it's connected with the specific weather types. High temperatures are associated with high pressure systems, and these are also days with a high radiation where you can build ozone. And so we have, for one, a single exposure to temperature or to ozone, but also a combined exposure. And here I show you a study from one of my PhD students. She looked at those combined events, health-relevant combined events, and she combined a temperature maximum with a 75th percentile with a threshold, because below can assume that there are no health impacts, but above this we have specific health effects from temperature, heat effects. We also took the 75th percentile of ozone, and as well as a heat-related threshold. And in the left figure, you see that about 16% of all days in the spring and summer season, as average across Europe, are such ozone temperature days, where you have these high temperature and ozone levels. And then on the next figure here, you see that about 66%, so about 2/3 of all days in summer are hot days, or of the hot days are also ozone pollution days. So when you have heat, you commonly also have ozone exposure. And here you see the projection for these health relevant ozone temperature events until the end of the century. Now this plot shows you under the RCP 8.5 scenario, very pessimistic scenario. And under this pessimistic scenario, we see a strong increase of these events, and amounts to about 40%, 78% increase. So then about 25% of all summer days are ozone temperature days. And the strongest increase we see here in South to Mid-East and Central Europe. So now I want to go particularly into the urban areas, which are the focus of this panel. And first of all, we have maybe you know this picture where we have in cities a kind of background concentration of pollution, which comes from the long-range transport and more regional emissions. And then on top of it, we have the urban emissions. And then we have specific peaks in air pollution in the cities coming from the traffic. So traffic hotspots have the highest pollution. And this is for sure valid for particulate matter or NOx. But if it comes to ozone, it's different, because at the traffic sites we have relatively low ozone concentrations. This is due that we have the chemical reactions with NOx, so you have a fast buildup of ozone, but also it's fastly destroyed. So and then when you go away from the traffic hotspots, ozone concentrations increase rapidly and are highest in the urban background or then even in rural areas. And I also want to highlight this with this study. Here I looked at ozone concentrations in cities of Bavaria. This is in southeastern Germany. And it's divided now by different types of station characteristics. And we see it's a projection under climate change, and it's the difference between. So I think now the slide switched away. So I go back here. And so you see in the numbers give you the projected frequency of exceedances of one for temperature for hot days, and on the other hand for different ozone levels. And here as a threshold for ozone, 100 micrograms per cubic meter air were chosen. As also a health relevant threshold is a threshold which is recommended by the World Health Organization. And we see that until the end of the century, hot temperatures occur very frequently at urban traffic sites. About 30% of all days are hot days, and it's an increase from the historical period of about 25%. So in this regard, you see how important or how significant the temperature increase is, particularly temperature extremes are under climate change in Central Europe. And if you go to the rural regional background, it's still 28% of all days which exceed a temperature of 30 degrees. And if we look now at ozone, we see that at the urban traffic sites, it's a high amount, about 40%, but then when we go to the urban background, already almost 57% of all days are high ozone pollution days. And we look at the combined extremes, we see that about 30% of all days will be high ozone pollution and hot days in the future in Central Europe. So now I would like to come to some future research directions. If we look at cities, the heat problem is strengthened by the temperature extremes and also by the urban heat island. So cities are hotter than their surroundings, and there are many studies look at not only the temperature effects in the city, which is shown here on the right-hand side plots, where we have, for one, the temperatures within the city. In the upper figure, under a small or under a moderate scenario of climate change, and the lower figure one shows under RCP 8.5 conditions, like strong climate change scenario. And it's with regard to health, it's important to combine it with the vulnerable groups in the cities. So this is shown here by the people index, which gives you measures like population density, fractions of vulnerable people like children and elderly people, or people who are living alone. And also the place plays a role, like how much is sealed area within the city, how many green spaces do we have to mitigate the heat, etc. And this is a research direction which is very advanced for temperature, but at ozone we see differences, because here, as I showed before, the hottest or the are not in the centers, in the most sealed areas of the cities, but it's more a suburban problem. And so it will be necessary to combine the information on heat, on ozone pollution, and also on different aspects of vulnerability. So that's it. Thank you very much. And I look forward to the discussion later.
Thank you, Professor LK. This was very enriching, and it also highlighted that we are also caught up in a situation where we have to kind of look at these research questions and these different notorious pollutants in a different light, wherein reducing PM 2.5 might lead to ozone or the other way around. But we'll come back to all those questions maybe in the round following the presentations. Thank you very much again for the very enriching presentation on the ozone and its health impacts. Now I would like to move on to Dr. Sunil Gulia, who will be presenting on the impacts of COVID-led lockdowns in India and other research about particulate matter levels and what do they mean for Indian population, their health, and the urban centers we are living in. Over to you, Dr. Guli. Much. And I will request other speakers to please mute themselves so that the presenter can present the work. Thank you.
Okay. Good evening again to all the Indian and other Asian countries fellow, and good morning to the others part of the Europe, all the participants. So myself, as Dr. Deya already introduced me, so I'm today going to present some of our institute work on air quality in Indian cities, and what would be the agenda for air quality management in Indian cities and other cities having a similar kind of problems of air pollution. Okay. So the content of the presentation would be like some of the reflections of lockdown activities on air quality in 46 cities in India, and then what during that period we found that issues of high background levels in Indian cities, because as we are in the tropical climatic conditions, so there are lots of natural background concentrations we found. Then I'm going to highlight some of the points why we need the revision of National Ambient Air Quality Standards of 2009 and how the importance of categorization of continuous ambient air quality monitoring stations is required. Then for the future, we should go on the airshed management approach for air quality management in Indian cities. Okay, so this is the work which we have started after one period, and in this work we have selected some of the CAQMS stations. Almost 58 CAQMS stations have been selected to analyze the data of PM2.5 and NOx. The 46 cities throughout the India, wherever there is a stations available, we try to collect the data and analyze that. And almost we have divided the stations based on the zone-wise, like northern, eastern, central, western, and southern India. And further also we have divided the cities based on the population density. It is already published in one of the journals. And then the selection of the CQMS is very important, and then we have selected that wherever there is a availability of active CQMS stations, because there are many active CQMS stations there in the India, but some of them are not active, so they are excluding from the study. Then city has been divided into small, medium, large and mega cities, so that we can see that, because in the lockdown activities there is one source which is active, like domestic emission, which is directly correlated with the population density. Okay, so based on the by thinking that considerations and all, we have categorized the city based on that. The location of the city, because the meteorology in Indian conditions vary when we compared to north to south and east to west. So we have divided the CQMS based on that, and that we have considered the period of March 1 to 21st March as a pre-lockdown period, and March 25th to 19th April as a lockdown period. And then we have compared this data. You can see in the tables about the distribution of number of stations in different zone and different cities, class of the city. Yeah, it is before analyzing the data, it is very important to analyze the meteorological difference, because we have selected two periods. One is pre part of the March and then later part of the March and April. So there may be a slightly change in the meteorology which can impact the dispersion by potential of the area, and that can be kind of reflect the issues of quantification of the impact of lockdown activities. And we have compared the wind speed, wind relative humidity, and ambient temperatures for that, and we found that there is only 5 to 6% of the difference in the meteorological condition, which is, we can say, it's not so much significant. And when there is a significant difference, we found we have excluded that statement from the analysis. So after that, you can see that there is the graph is showing that concentration during for the PM10 and PM2.5 and NOx for different zones of the countries, and you can see that the blue line is showing the average pollutant concentration of that station for the pre-lockdown period, and then red is showing the red line is showing the lockdown period, and you can see the difference in different kind of zones. But this difference or the impact of lockdown activity is not homogeneous throughout the country. There you can see in the central India, like cities like Bhopal, Kashmir, what are the states of cities of MP state, the central part of India, does not have much impact on the PM2.5 and in the NOx also. So in the PM2.5, we can say that the location of the PMS is very important, and maybe the natural background, natural concentration, maybe always a little bit high, which insignify the impact of lockdown activities. Means that I just explained the lockdown activities because there is no sources are active that can accept essential services like industries and some of the medical facilities and all. Otherwise, everything was closed. That means this is the level where really never going to be achieved again, or maybe that. If we plan any kind of restriction of the activity, this is the best time when we have already closed everything and we analyze the data, but still we found there is a high level of there is a level of concentration which is need to be worry and think about that how much we can reduce it more. Okay, and you can see that the PM 2.5 concentration reduced by about 34% in northern states, 17% in the eastern part, but there is no reductions in the central India, and 31% in western India, and 26% in southern zone. We have found that. And if we talk about the based on the population of the city, we found 23% in the small city, 16% in the medium, 32% in the large, and 28% in the mega city. You can see that the large cities have more reductions in this. Similarly, NOx also, but the reduction percentage is totally different in the case of NOx compared to PM 2.5 because the sources are different for that. This is just only the pictorial view where that pink bar is showing the pre-lockdown PM 2.5 concentration and blue is showing the lockdown concentration. You can see that, and the numbers also, how in the northern India there is a high reduction compared to central India and southern part of the India. And this is only due to maybe the methodology and contributions of natural sources. Then we have done from the same data, we have categorized based on our understanding and based on some of the images from the Google and taking the actual coordinates of the system, what's the background stations, residential, commercial stations, or curbside or industrial stations. As per regulatory norms, we don't have any background stations out of them. But if we want to compare something like that, what can be the representative stations which will be? So we found that in the background station we selected some of the stations which have no sources in the current vicinity of the stations, very less possibility of transport from distant sources, emissions from the scattered residential activities, because these stations are not located in the residential activities. So out of 50 stations, we have found such 13 number of stations, and 20 is the residential, curbside 25, and we compare the average concentration of PM 2.5 and NOx in these stations, and we found that whatever we have selected as a background station, the average pollutant concentration is less compared to the stations located at near to residential and curbside or industrial locations. Then we have compared the average pollutant concentration during the lockdown period of these 13 stations, and we compare these stations with the percentage of national ambient air quality standard, and you can see that already it is 25% to 60% of already we have a kind of background concentration at these stations. It is already there. So whatever it shows how the natural sources are contributing to the current level of pollution in the pollutant concentration, which attract and put a question on the need of the revision of the national ambient air quality standards for Indian conditions. Indian government has already put lots of efforts on the control actions for the air pollution, starting from 1974 when they have started the Central Pollution Control Board establishment, and then there is the Air Act in 1981, and then Environment Act in 1986, Then notifications about the air quality standards in 1994. We have first time introduced the ambient air quality standard in 1982. So there are lots of effort has been put in by the government in the different sectors of in different sources and regulations and monitoring techniques to act for the better air quality. This list showing the concerns of the government regarding the air pollution control activities. But still, we have to go far and find out the exact solution so that we can receive some of the better practices of the control action. Now, NIRI, my institute has doing some of the analysis at 3 locations in Delhi from last 20-25 years, and we have data of that one. So out of that data set, I have compared some of the progress in the improvement or in the degradation of the pollutant level concentration, and we found that if we compare the pollutant concentration with respect to 2005, there is a sharp increase in the NOx concentration by many-fold. But there is a reduction in the SO2 concentration, and also there is not much change in the PM10 or RSPM concentration. And if you categorize the same in the same time period, the control actions put by these different control actions, you can see that. Now the new approach which I'm thinking, or my team is here thinking to put that what should be the future for the air quality management point of view for Indian cities. There should be a airside management, which already some of the developed countries has adopted that and found some successful success in reducing the pollution level. This is the framework which we have applied in one of the studies here in Delhi NCR, and we found by analyzing all the components which are directly or indirectly related with the air pollution dispersion and the pollution formation, we have included in this one, like LULC profile, elevation profile using GIS tools, then meteorological data by WRF simulations, and IMD also we have taken and analyzed and find out that based on the meteorology what would be the airside for the study region, and at what sources we should focus more and give priority so that they can be give a better result if we need to put any kind of management action. So instead of putting in the whole study area or Indo-Gangetic plain, let's focus on the airside management approach and put more maximum of the efforts on that direction. And we found some of the critical districts in the study region where the air sources are directly impacting the air quality of Delhi. The pictures which is for the month of January, February, and March, you can say a kind of winter period, where the airside has been defined based on regional, medium, and micro scales. You can see the different color coding that can be in the area where the management plan like GAP can be implemented and see the most effective result of that. As we know that there is a air quality monitoring station. This is just the slide which is highlighting the how we should go ahead in future. We all know that we have a huge heterogeneity in the sources, every type of sources, which is not in the other part of in the western part of globe, but here we have a huge variation in the sources. So accordingly, we have to categorize our monitoring stations and networks based on the source oriented, background oriented, and research purpose also. That kind of things we have to bring out that. I'm also in the end. This is the last slide, highlighting one of our efforts in the compilation of the past studies done by Indian air quality research. Then we have compiled and made this website called Ind-Air, where you can find out all the studies related to Indian air pollution starting from 1905 when the first time Bengal Smoke Act has been introduced and enforced in that one. So that's from my side, and thank you, Dr. Daya, for your introduction. Thanks.
Thanks, Dr. Gulia, for enlightening presentation, and it was really good to see the emphasis on the regional aspects of pollution, as well as looking in detail into the background consultations. I myself have a few questions on this, and I'm sure there will be more questions from the participants. But we'll come back to the questions after next presentation by Dr. Hang. But before that, just a correction: I'm not a doctor. Yeah, I didn't do PhD. I've been working. So that's the correction. And now moving on to Dr. Han. Dr. Han will be presenting on the chemical transformation of the aerosols, and we look forward to an interesting presentation, Dr. Han.
Thank you, Suni, and thank you for coming to my talk. So my topic today is about science-oriented emission control and environmental policy making. Take a breath. Even if the air looks clear, you will still inhale millions of solid particles and a liquid droplet. These airborne particles and droplet are known as aerosols. Atmospheric aerosols come from both natural and anthropogenic processes, such as dust, sea salt, volcano eruptions, and all kinds of burning and combustions. So they are everywhere, drifting from the Earth's atmosphere, from the stratosphere to the surface. So the size of atmospheric aerosols vary from a few nanometers, so less than the viruses, to several tens of micrometers, about the diameter of human hair. So despite their small size, they have a major impact on our climate and also on the human health. So for us, we breathe about 10,000 liter air per day. So it's inevitable that aerosols in the air is highly relevant for our health. And together with other air pollutants, it has been ranked as the top 5 leading health risks worldwide and show strong influence on mortality over vast areas of the continent. Moreover, aerosols have also very important climate impact by either cooling or heating the atmosphere. And they can also modify cloud and precipitation. So it's these very tiny aerosol particles that make the scene in Beijing look so different compared to a clean day. So for the climate, you can find that the cooling or warming effect by aerosols can be indeed comparable to the greenhouse gases, yet with very large uncertainties. So it's very important for us to understand, or not only to understand, but also to predict the formation, fate, and the impact of atmospheric aerosols. So from emissions, transport, chemical reactions in the atmosphere, to haze, climate, and health effects, as well as the biological effect on natural resources. So there are a lot of reactions and interactions in the atmosphere. So these chemical, physical, and or even biological process involving gas, particle, and other gases, they constitute a close link between human and the ecological environment, and between air pollution and climate change. So today, I will give some examples how a better scientific understanding of these processes can help policymakers and help us to achieve the common goal of cost-effective pollution control and climate mitigation. So the severe haze shrouding Beijing in cold winter recalled the memories of the London killer smoke. So in December 2015, Beijing issued its first air quality red alert. It urges the need of effective control strategies. So we can, of course, simply cut the primary emissions, right? This is the general idea. But can we act beyond that with the help of chemists? So to control the air pollution, we first need to know where these aerosol particles come from. So except for direct emission, secondary formation is another very important source. So I think there's something wrong. Yeah, but it converts the kind of gaseous air pollutants, such as SO2, NOx, and VOCs, into aerosols like sulfate, nitrate, and organic matters. As we know in China, like up to 80% of the PM2.5 are formed through the secondary formation processes. So if we can block the secondary formation pathway, it will also kind of help us to remedy the PM2.5 pollution. The question is how can we do that? So from a chemical point of view, secondary aerosol formation, so the conversion from gas to particles, is an oxidation process that convert the compound of low oxidation state to high oxidation state. So that's why identifying the oxidants and their origins become a key to understand these aerosol formation processes and to control the PM2.5 pollution. So to answer this question, if and how we can block the secondary formation pathway, we first need to understand the haze chemistry. However, during the haze event in China, even simplest as the sulfate, we seem not very well understand its formation mechanism and the key oxidants. So according to this kind of conventional understanding, in polluted areas, sulfate is mainly formed through photochemical oxidation of SO2 by OH radicals. So therefore, when aerosol concentration increase, we would expect a reduced sulfate production rate because of the surprise photochemistry due to aerosol dimming effect. But in reality, the observations show a very strong enhancement in sulfate production, suggesting a missing oxidation pathways. So even with other kind of cloud chemistry included, the model can only kind of capture like 10 to 20% of the observations during the severe haze events. So when exploring this missing pathway, we found that the high missing sulfate production, as indicated as a difference between the observed and model sulfate concentration, was always accompanied by the high aerosol water content. So follow this line, it turned out that the reactive nitrogen chemistry in aerosol water, so the right circle mark here, can largely explain the missing source of sulfate, so the white diamond, and exceed the contribution of photochemistry, so the green cross, by order of magnitude during the severe haze events. So in this mechanism, aerosol water serves as a reactor, and the alkaline aerosol components trap SO2, which is then oxidized by NO2 to form sulfate. So in contrast to the negative feedback of photochemical aerosol formation, this new reaction in aerosol water has a positive feedback. So the more aerosol produced, the faster the reaction goes, and then you have more severe haze pollution. So coming back to the early question, can we benefit from knowing this detailed chemistry? The answer is yes. So we can block the oxidation pathways through target emission control, in this case of NO2. So since NO2 is not only an oxidant of sulfate, but also a precursor of nitrate, so cutting NO2 through cutting NOx will reduce both sulfate and nitrate, so which is a more effective solution because of this large co-benefit. So this series of studies have led to several hot and highly cited research articles, and also they have attracted the attention of policymakers in China. So follow this line, we can see that this kind of a reaction in aerosol water strongly depending on the aerosol pH, as shown here. And the key oxidant may also change. They can change from NO2 to like this kind of transition metal catalyzed reactions. Then when we ask whether this NO2 pathway can be maintained because we see a fast production of proton in this reaction, right? This is going to change the aerosol pH. So this question actually also are pushing us to further explore the mechanism that control aerosol pH in this polluted environment. So we first just perform model simulation to test the response of aerosol pH to the acid addition. So interestingly, unlike a normal water solution, so the dashed line is not a kind of like water solution, all the investigated aerosol system show a rather weak response to the addition of acid, suggesting a strong buffering effect. But we can see that they are buffered at different pH. So how and why it is buffered, especially, what are the buffering agents in aerosols? So according to this kind of classical buffer theory for solution, each buffer agent has a characteristic buffer pH. So the diverse pH of different aerosol systems apparently suggests different buffer agent. So to check this, we calculate the buffer capacity for individual potential agent, as shown here. The buffer capacity is defined as the amount of acid required to change aerosol unit by 1 unit, to change aerosol pH by 1 unit. So the results are interesting. So on one hand, right, the aerosol pH are indeed close to the peak buffer pH of each agent. But surprisingly, right, we see 4 unit difference of this kind of buffer pH. But then they point to the same agent, ammonia. So this means that actually one agent, buffer agent, can have multiple buffer pH in aerosols, which is different from what we understand for a kind of standard solution system. So to explore what drives this difference, we have derived this kind of analytical expression of peak buffer pH for multi-phase systems, but you don't need to go into detail. So note that in solutions, right, the peak buffer pH is kind of pKa. pKa is the acid dissociation coefficient. But for a multi-phase system, it's almost the same expression, except that the pKa is replaced by pK star. So pK star is not only a function of Ka, but also depends on the aerosol water content and temperature. And globally, over 70% of urban polluted areas were buffered by this ammonia agent. You can also think of it for India, right? Ammonia is also kind of a hotspot. So in this buffer regions, the variability of aerosol pH is merely controlled by the difference in aerosol water content, where the difference in chemical composition actually play a rather minor role. However, in the non-buffer regions, it's the opposite. So together with our previous discovery of soil recognition emissions, our result here give another example of the buffering mechanism in the Earth system, representing a close link of atmospheric multi-phase processes to the pervasive human influence on ammonia emissions and the nitrogen cycle in the Anthropocene. So at last, I will give an example about the great importance of clean energy supply and the importance of efficient coordination between environmental and energy agency in achieving the common goal of air pollution control. So significant improvement of air quality has been achieved in China since 2013. So this is largely due to the control of dispersed coal use and also the use of clean energy. So to fight the severe heat in northern China, I think that's one of the most polluted environment 5 to 10 years ago. The government has implemented coal to gas and coal to electricity strategies in these regions. And it has been intensively implemented, especially in these 2 plus 26 cities in northern China in the winter of 2017. So here we show that on top of the meteorological influences, so we have corrected the change of meteorological conditions, these emission mitigation measures achieve on average a kind of 14% decrease in PM 2.5 concentrations in Beijing and the surrounding areas in the winter of 2017. So I mean, compared to the same period of 2016. So the dispersed coal control measures itself contribute around like 60% of the total PM 2.5 reduction. So it's kind of very effective measures. However, the localized air quality improvement in northern China was accompanied by 15% simultaneous upsurge of PM 2.5 in southern China. So you can also see from this figure, it's very clear. And they are dividing by the north-south central heating supply line. So this shows a clear regional redistribution of air pollutants. As our model has accounted for the difference in meteorological conditions, so the high PM2.5 in southern China is a clear sign of the increased emissions. So, but why? So our result point to an unexpected but reasonable explanation: the shortage of clean energy. So the coal-to-gas policy in northern China require more natural gas supply. However, in 2017, for whatever reason, China suffered from overall shortage of this natural gas. As a consequence, southern China, because we have to ensure that we have the good air in the north, right? So therefore, we ensure the supply of natural gas there. But southern China was forced to undergo a transition from clean gas energy, then to more use of this kind of dirty coal. So therefore, I mean, all of this resulting in worsened air quality in southern China. And here you can also see that in 2018, when there is no natural gas shortage, the redistribution phenomenon disappeared, showing a nationwide air quality improvement. So I think this story actually demonstrates the importance of coordination between environmental department with energy department, and also the importance of energy security. I think this is especially relevant for China and India. So our research aims at improving our fundamental understanding of atmospheric chemistry. So the improved mechanistic understanding will lead to more kind of accurate representation of these processes in our models to address the grand challenge of actionable projection of future environment in the Anthropocene. So for that, actually, we normally combine lab and field experiment as well as some instrument development. And most importantly, we then take integration and the synthesis approach by applying and developing multi-scale modeling tools. So the key has always been identifying and bridging important gaps between observations and models. So that's why we are always thinking that the observation network are especially important and valuable. So this actually often reflect, because the difference often reflect an imperfect knowledge in our understanding of this kind of atmospheric system. So with such approach, our research involve multiple aerosol physical and chemical processes, where we discover the key roles of reactive nitrogen chemistry and the multi-phase buffering effect in controlling atmospheric oxygen capacity and heat formation. So another focus not mentioned today is the phase state and the phase transition of aerosol particle, which also largely regulate the aerosol fate and their kind of global impact. Moreover, we show the importance of mitigating short-lived climate agent like black carbon and how our scientific understanding can contribute to the policymaking. So we hope that our work could also contribute to the improvement of air quality in India. And we would also like to collaborate and jointly work out this issue with our Indian partners. So with this, I would like to close my talk. And also I would like to really thank my group members, partners, and also several different funding agencies. Yeah, so that's all of my talk. And thank you for your attention. And yeah, I'm very happy to take questions.
Thank you, Dr. Hang. This was indeed a very, very good presentation, and I would say it's very timely as well, because right now there are lots of policy issues which are opened up and which are ongoing, which will definitely benefit by looking at your work more particularly into the energy sector and coal-based power sector, which is aspiring to go for cleaner technology deployment in the coal-based power plants, but there are different kind of resistances which have been faced. Thank you very much again for a really interesting presentation, and we'll come back to the questions. Right now, I saw that there were a few questions from the participants to Professor LK, and she has answered those. Until we have further questions from the participants, I would like to go for a round of questions to each of the speakers based on the interesting work described by them. To start with, Professor LK, I had a question based on your presentation where you were kind of mentioning that NOx is already very high in the cities, and because of NOx being high, it's the limiting factor is VOCs in the cities. So how do you explain that the NOx levels which are already existing in Europe as well as in Indian conditions, because that's not a limiting factor, but you said that that's not a limiting factor because it's already very high. So what are the levels which you believe should be in terms of regulating NOx, so that there is less buildup of ozone and health impacts arising out of it?
Thank you for your question. It's not that trivial to answer that question, because ozone production depends, for one, on the precursor emissions, and these are not only the NOx, but also the volatile organic compounds. And so it depends on what kind of regime you are. Are you in a city where you have very high NOx levels, then it further increases of NOx won't do anything for ozone formation. And so so the contribution comes from the volatile organic compounds. And if you lower now the NOx, you have to lower it so much that you come in an NOx sensitive regime. And per se, it's not a fixed threshold, but it depends on the location. But I want maybe to answer this question from the health point of view. And here we see that NOx, that the threshold is at 40 micrograms per cubic meter air. So we should definitely come below this threshold in order to avoid health impacts from NOx. And when we come down this threshold, we also lower down ozone formation, because then we are also lowering down the precursor emissions. So it's a kind of win-win situation for health impacts from NOx and from ozone.
Thank you, Professor LK. That's definitely true that there is win-win for not just NOx reduction but also for the ozone reduction. And that takes me to the other question which Dr. Hang was also mentioning, that when we look at the pollutants, we mostly end up looking at just the primary pollutants, and even when we look at the secondary pollutants, particularly for SOx form, sulfate formation, we look at the SO2 emissions and not at the NOx emissions. But you very interestingly also mentioned that NOx concentrations are also a governing factor in the sulfate formation, and that's why combining the two presentations, if I can say that reducing the NOx concentration will not only reduce NOx and nitrates, but it will also lead to a reduction in the ozone as well as in the sulfate formation. So, Dr. Hang, I would like to ask you, so till now, when we know at certain locations, more particularly in India, because we are right now conducting a research, and in that research we have found that about more than 95% of the total PM contribution by coal-based power plants in Delhi NCR region is from the secondary particulate formation, which are basically sulfates and nitrates. So, how important is it to regulate not just one gaseous pollutant or not just the primary pollutants, but a combination of all these factors? And would a policy decision be helpful in cleaning the air if we just focus on the primary concentrations of these primary pollutants in isolation? Or do you, Professor Ham?
So your question is how can we really kind of coordinate the emission of all this from
Let me give you a little bit of more background. So right now in India we have emission standard for coal-based power plants, which were kind of notified in 2015 December. And this was the first time when Indian power plants had limits for SO2, NOx, as well as mercury emission, because before that we only had regulations for the PM. But over the last 5 years, the NOx regulations have been diluted significantly from where they were it was asked for the power plants to regulate NOx emissions below 300 milligrams, but now that has been kind of diluted to 450. And for the newer power plants, the limit was 150 milligram, and that's also seems to be going in the direction of being diluted to 450 milligrams. And on the other side, for sulfur dioxide also, there is a new argument coming up from the government which says that if the concentration, primary concentrations of SO2 as a gas is less in a region, then the power plants in that region doesn't need to install SOx control instruments or FGD for that matter. So how valid do you think such an argument is, and do you see an imbalance or lack of coordination between the energy department and the environment department, similar to what you might have seen in China when you were doing this research for last 10 years?
Okay, yes. So because I think this might be different from the kind of the NOx, the NO2 pollution, because for NO2, there seem to be kind of a threshold for the healthy impact, but actually for PM 2.5, even if you have very extremely low concentration, right, you don't see a clear kind of a threshold. So this means that I'm just considering the health impact, even if the precursor like SO2 is not extremely high, it's still worthwhile to kind of further reduce, if possible, its emission. And also, the lifetime of SO2 actually is quite long compared to NO2, and also, that this kind of regional transport could also contribute not only the local areas but also over a large region. So therefore, I think for the power plant, according to our experience, that the control of power plant is actually the easiest and the most effective way to reduce the emissions. So therefore, in this case, I would suggest that even if for the relative clean areas, it's still worthwhile to reduce the SO2 emission from power plants. And also, for the NOx emission, I think it's indeed a bit complicated because our calculation apply for the winter Beijing because of this kind of multi-phase chemistry. Is especially important when you have a lot of aerosol and also when you have very cold weather. But for India, I think we need to double check if it's in a similar regime. And also, I think like Professor Hettig's concern about ozone is also a very valid question, because the NOx also have a kind of a different impact on ozone formation. I don't know for the case current case in India, but in China, in many cities, if you reduce NOx due to this kind of nonlinear titration impact, if you the reduction of NOx will lead to this kind of increase of ozone pollution in several like winter seasons or in the spring season. In summer, I think we are still checking. It might be okay, but it's still not clear. So therefore, I think for NOx, it may differ between different region areas. But for SO2, I think it's very safe to largely reduce that.
Dr. Hang. That's very interesting. And you also mentioned about the regional aspect of these pollutants. And Dr. Gulia, in his presentation towards the end, mentioned that right now the approach which has been taken in India, not just with NERI but with many other research groups, is to look at the pollution sources regionally and look at the larger data set. So, Dr. Gulia, I wanted to bring you in here and ask you a question, not directly on the presentation, but on the policy direction in India. As you rightly mentioned that till now in India we didn't look at the larger air set approach to regulate the pollution, and even plans like rapid response action plans were very reactionary in nature. So do you believe that now when the government institutions like NERI or other research institutions which have started backtracking the larger air set in terms of where the pollution is coming from to a particular location. We know that we have a very decent inventory of the industries, their emissions and locations. Do you feel plans like ready response action plan can be made more precautionary or anticipatory rather than being reactionary with such knowledge, wherein maybe a few days, 4 5 days in advance, we can tell that there is a air mass which will be traveling over these regions and these industries or these pollution sources, and if we shut them down or operate them at a lesser rate or operate them in a more cleaner way, maybe the pollution episode and its severity might be reduced. So do you think we as a research community and as a policy direction in India are moving towards that?
Yeah, thank you. Very nice questions, Sunidhi. Actually, the important is that definitely we should, based on the, instead of reaction based, we should be more proactively should implement the actions before the episode happens. Actually. But the graph is like that. Once the episode happens, then it's the action starting. So instead of we are waiting for October, we should start our activity in the end of September or something like that, so that we should not reach the level which we are always from the last 5 or 6 years we are getting in Delhi NCR. Regarding the applications like Delhi NCR, the graph is designed for Delhi NCR region, which is a very high, large area, and definitely if you see the apply the airside approach, that area all like in the south of Delhi and like Rajasthan, two districts of Rajasthan and southern part of Haryana, they are actually not much impacting their air quality because the wind is not flowing from that direction towards Delhi. Okay. So I think instead of applying the whole NCR area, which is very large, and definitely if you are work on a large area, you need more efforts and more activity, and then there may be a lack of some kind of monitoring and implementation. So instead of so much of large area, you just identify based on some based on the science, you should identify the area and then focus more towards that area with good force and all. Definitely, you will get a good result instead of what we are doing presently. So that definitely will work if we go in that direction. And then second thing which regulators should focus more on that, we have many stations here in Delhi NCR, and some of the stations are located just in the premises of the high density sources. Are we really need to see that these are the ambient representative stations? As a research community, we should speak that these are the source-oriented stations, and this should not be compared with the ambient standards. So that categorization we have to do that. So I think precautionary actions are more beneficial than the reaction based like that. So I think that it is good that we can start the activities before October.
Thank you, Dr. Gulia, for that answer. Now, coming back to Professor Aded, I would like to ask you, you mentioned about the heat effects or heat effects and ozone's relation to that. So, do you think in India, the research community still has not kind of focused much on the heat island effects and the increasing temperatures. But we have very clearly seen that heat episodes strike in India in the summers, and most of the central Indian region, cities like Nagpur faces severe heat waves, and there are clear health implications which are visible on the roadsides, people dying because of the heat waves. So, can you shed a bit more light onto the heat and its health impacts, as well as the importance of green spaces in our cities in relation to the ozone formation as well as to the heat effect?
Heat is a problem which will become even more important now under climate change, and projections say not only for Central Europe but also for India strong increases of heat events. And if we look at cities, we have here concentrated the population, so that's one thing. In cities we have many people, so many people are exposed. And then we have the specific urban heat island, which comes from the built infrastructure. It heats more than the surrounding area. So we have, in principle, two effects for cities with respect to heat. We have the urban heat island and climate change. And then it's heat events or heat thermal load is not equally distributed in the cities. Where you have lots of green space, temperatures are lower, and where you have a lot of sealed areas, the temperatures are quite high. So a lot of urban green mitigates the effect of heat, which is actually good. And but now it comes also down to the population which are affected. And here many factors play a role, like, for instance, the socio-economic position of the population. If you have more money, you have a nice house with a lot of green areas. And if you're poor, you live in a bad housing and a very highly sealed up area, for instance, and so on. And if we look now, this is a part of science which is quite good explored, at least for the European cities. But if it comes also to the ozone events, and what I showed before, we have many events which are combined events. You have a high heat load and high ozone pollution. And now if we look at the heat events in the cities, they are mostly concentrated in the densely built up areas. But it's not the space where we have the highest ozone pollution. The highest ozone pollution we have in the suburban areas. That's the situation right now. And the future climate change, also the suburban areas will see a considerable temperature rise. So they are now affected mostly by ozone pollution, but in the future they will also be affected more by heat events. And so it will be necessary to mitigate both. So we have to introduce green spaces in the densely built up areas to mitigate the strongest heat events, but we also have to think about measures to reduce the ozone pollution.
Thank you for that answers. I'll move on to Dr. Gulia again, and my question to you is that you mentioned that even during the lockdown, when most of the consultations were representative background consultations, the pollution levels of PM2.5 levels in the range of 25 to even 65% of the national ambient air quality standards. And based on those findings, your suggestion, one of the suggestions was to relook at the national ambient air quality standards. But to play a devil's advocate kind of role, we also know that India is a geography where residential emissions contribute a lot, and even when we were in the lockdowns, the residential sector was definitely contributing to the air pollution levels, maybe not to that level where it was, and not all the industries were closed down, but yes, there was a very significant and clear drop in the industrial activity and even in the power generation sector. So while taking the background considerations for this period, I'll still when looking at your data for different stations in different cities, we also saw that the cities in the north definitely had higher pollution levels even during the lockdown. And you also spoke about the regional contribution, and Professor Etek also mentioned that there is a background, that there is long range transport pollution level, then there is regional pollution, and then the cities pollution, and on top of that we have these hotspot traffic hotspot areas which contribute to pollution. So understanding all that, is it don't you think we should look into more long-term trends, maybe a year-on-year kind of analysis before kind of suggesting revision of ambient air quality standards, just based on what we can, what kind of pollution levels we got, rather than based on the what kind of health impacts will we have at the prevailing pollution levels, even if they are so-called background pollution levels, which are not really the background pollution levels. So, how do you answer this riddle when yes, we looked at certain data, we had certain research, but we don't have enough data to reach a conclusion of whether the emissions, whether the ambient air quality standards should be revised towards the upper side or lower side. What's your take on that?
Yeah, I fully agree that with you, Sunil, because to analyze and revise the large policies based on a 1 year or 2 year data is not sufficient. But that kind of things, I think for that we should put some kind of permanent background stations where we can analyze and to see some of the yearly trends over there, and then based on that we can take a decisions on that. But if you look about the other countries in the US and Europe, you will find that in every 10 years and in interval of 12 years, 15 years, they have to change they have revised their standards, because there are lots of technology has been improved in that sort of period of 10 years, in terms of monitoring technique and in terms of control options also. So I think by considering all that things, it is a good time of a year, 10 to 12 years or 15 years to change and revise the standard. Now we initiated a national amendment for the standard in 1982. Then after that we have revised it in 1994, and after 1994 we have revised it in 2009, and now it's almost 11 years, 12 years happened. I think the community should think about in that direction also. And regarding few of the stations like in Delhi are running more than 12 years, the continuous stations, and we have a set of ambient manual stations also under the National Ambient Air Quality Monitoring Program, where throughout the India the pollution control boards are monitoring more than 30 years. So by examining that data, it can be useful and take a decision to think that what should be the ambient air quality standards and what should be the accordingly the classification of the monitoring station. It's not like that if we are putting one station at curbside and we are comparing it with the national ambient air quality standards. I think that's not a right approach to see that. And it is also like if you see the air quality index also. The air quality index generally represent the compare the whatever the stations or numbers of data we have. It evaluate and put the maximum AQI is the AQI of the city as per the guidelines of the AQI. But that actually not the actual AQI of that city, because that's due to only the local sources which is just looking putting near to that source, interesting source. That's in my view, it's a time to think about the revision of the standard, and it's not like that. See, in one go, it should go. It should be with the discussion of the various stakeholders, with the different stakeholders, even though involving of the public also and health experts also. Yeah.
Thank you, Dr. Gulia, for that. And just to let you and other people who have joined the discussion know that there is already a process which is in place, which involves Central Pollution Control Boards and various other institutions, including IIT Kanpur, which have started. That group has started looking at revision of the ambient air quality standards in India. So that's already ongoing. We have just four minutes, and I would like to take one last question for Dr. Hang, and after that, if Dr. Hang can summarize that in 1 minute and also add in any final comments. Which can be followed by final comments by other speakers before we close. So, Dr. Hang, I understood from your presentation that while looking at the air pollution policies and climate change policies, we should also look at the energy policies. And one clear example was the shift to natural gas and scarcity of natural gas led to high pollution levels. So, do you think when we have renewable energy sources which can be deployed in a decentralized way and locally, there is a time to maybe not even think about gas being the bridging fuel and make the transition directly from coal to the renewable energy. Is that the way we should go forward looking at the air pollution, climate change, and health impacts? Your final comments.
I think to move for clean energy is definitely the future, but the question is, how fast we should move in this direction. The case that we found in China, and also, there are also some other cases indicate that the energy security actually is one issue that has been underestimated when making such kind of policy to try to solve the environmental problem. So especially I think this is important for country like India and China. So my kind of suggestion would be that this is the direction we should go. But before largely implementing such kind of transition, we should also carefully evaluate the energy security. For example, if there's some like what happened in the United States recently, if there's kind of a very cold weather, right? If this kind of a clean energy is as robust as this kind of coal and other kind of energy. Yes, and so that's all I think what people should consider. And sometimes I think for the environmental protection, too fast sometimes may even slow you down. So I think a reasonable solution and practical solution is kind of more important. Especially when we have very ambitious goal, I think we should also be extra careful about the security issue. Yeah.
Thank you, Dr. Han. That's really, really important. And energy security for countries like India, which are dependent on the imports for supply of gas, as well as it's suffering due to air pollution. There was a recent report released yesterday, and that report by IQ Air Visual kind of highlighted that 35 of the 50 most polluted cities in 2020 were still in India, and that's why it's very critical to look at synergies of different policies into air pollution, energy, as well as economic domain. So thank you very much. This was indeed a really, really interesting discussion, which covered the basic chemistry to the policy, as well as research analytical application of the data which has been collected over different geographies in India as well as abroad. It was a really enriching discussion, and I hope this initiates a few more new research ideas into the people's mind, that they start researching more on heat, more on implications of reductions of NOx, SO2, ozone, their interaction with health impacts, and we have more scientific evidence and base to move forward to the right policy in a more efficient way. Thank you very much, Dr. LK, Dr. Han, and Dr. Sunil Gulia for being part of the discussion, and thank you everyone for joining in. I would like to mention that DWIH also has different exhibition halls where all these different institutes which are participating as speakers, moderators, or panelists have also put out their stalls there or their corner where you can find out more about the research, the work they are doing. So maybe you all would find some time out to check out those exhibition halls and go through the research work done by different organizations and other opportunities available for collaborative work as well as new research ideas. Thank you very much. Have a nice day or nice evening in India, and have a good day in the European time zone. Thank you, everyone. Thanks.